All right, maybe kids were into 7-4 and looking at slope fields again and doing some reasoning using the slope field. So some of this is going to be a little bit of a repeat from what we did back in 7-3, but some of it is adding on a few more added features. So identify the particular solution that goes through a point. The figure at the right shows the slope field for the differential equation 1 minus xy. Sketch the graph of a particular solution that contains the point 0, 2. So all you need to do, and this is, I've seen this question on the AP exam before, is go to 0, 2, put a dot. And then stay within the cattle chutes to see what the graph would actually look like. Now you're making an estimation. You're trying to stay within the cattle chutes, but you can see it kind of narrows out this way. And over here, it does a little turn and comes this way. Label that point A. Okay, I can do that. Call it A. Something like that. You're making an estimation. Maybe I could have made this come down a little bit lower to go closer to that horizontal asymptote. But it's an estimation. You don't have to be perfect. Sketch the graph of a particular solution that contains the point -1, -2. All right, well, that's down in this neighborhood. Plot the point. Stay within the cattle chute and see if you can graph that particular graph. I can see it kind of comes down like this. Then it actually goes a little lower. And then it comes up and it horizontal asymptotes over this way. So there's what that guy would look like. Call that point B. And you say, okay, cool. That's it. That's all the first couple solutions want you to do. Number 2. This is all a process of elimination in these. The slope field for a certain differential equation is shown to the right. Which of the following could be a solution to the differential equation with the initial condition of 0, 0? Well, if I look at 0, 0, y of 0, when x is 0, y is 0, there it is at this place. And you can see there's 0 for all of those. So what could it be out of those? Sometimes it's easier to go to the picture to figure out some of the information. So you see how there's a whole big blank here? It's blank because they're undefined slopes. Now sometimes some books, and I've said this in the last section, sometimes some books will put the vertical lines there. They're undefined slopes. Or they leave it blank. In this case, they left it blank. So I know, I'm going to put this in the margin, I know I have an undefined slope when x equals -2. Now think about that for a minute. If there's an undefined slope, then that means that there must be a grouping where x plus 2 equals 0. Right, because x plus 2, if I solve that, I get -2. In other words, I have a vertical asymptote, a denominator at x equals -2, putting all these pieces together from pre-calc. So looking at your choices, can you eliminate anybody? Who does not have a vertical asymptote at x equals -2? And that would be C. C's out of the loop, right? You don't have that. This guy, he has vertical asymptotes. Now think about it. If I take that denominator, set it equal to 0, solve for x, I know I have vertical asymptotes at x equals plus or minus 2. Do you have a vertical asymptote over here at 2? Do you have vertical tangent lines? And you don't. So he's out of the loop. There you go. Process of elimination. Now you're down to 2. This one definitely has a vertical asymptote at -2. This one definitely has a vertical asymptote at -2. Does the tangent have other vertical asymptotes? Think of the tangent graph. Tangent graph is like a squiggle, and there's asymptotes at every pi over 2. And so I don't see any more asymptotes in this picture. This would have more asymptotes because the tangent would have to have more remember the tangent graph? I'll just graph it real quick. Tangent graph goes like this, but then it goes like that again, and then so on and so on down the line. So it would have several tangent lines. This picture does not, which means your answer is D. So it's a lot of process of elimination in the midst of these. And that's how you're best going to answer it. There's not really a whole lot else to say. Number 3. Consider the differential equation here and its slope field shown. Describe all the points for which the dy over dx is -1. And you say, well, when does that happen? Let me figure that out. Dy over dx is -1 equals x plus 1 over y. Solve it out. Cross multiply. -y equals x minus 1. So y equals -x plus 1. Nope, this was a, I wrote it wrong. This is a plus. This is a plus, makes this a minus. There you go. So you don't really even need to look much to the graph other than to verify that that's the case. And so you're going to have a slope of -1. Slope of -1. This would be about where -1 is if I were to look at this. If I'm looking across the line here, my slopes of -1 would be like right here-ish. Does that fit this? Y equals -x minus 1. Sure enough, your y-intercept's -1 and you got a slope of -1. That's about where you're at with these things. So your answer to the question is all points that fall on the line y equals -x minus 1. Because that's where my slope would be -1. My slope is -1, my slope is -1, my line is right there. Don't make them harder than they have to be. Now the next one's more intuitive. Last one. Number 4, explain why the following could not be the slope field for this differential equation. This one has a slope of -0.3 times y. So let's just say, what if y equals, I'm just going to pick a number, what if y equals 3? Then dy over dt would equal -0.3 times 3 or -0.9. Let's go to where y equals 3. See how y equals 3? It's fluctuating, it's changing as I look at that, where y equals 3. This means it's a constant slope at 3. At 3, it would be the same slope field all the way across. It is not, it's changing. So that means that, let me see how I wanted to say this. You can use a specific example, and that's what I guess we did with this one. When y equals 3, you just are looking for, explain why the following could not be. So you need an example where it doesn't work. It can be a general explanation or it can be a specific explanation. We're going to use a specific for this one. If y equals 3, then dy over dt equals -0.9, which is constant, and the slope fields don't represent that. Represent that at y equals 3. They're changing. You can use a whole lot of different verbiage to be able to explain it, but that's one possibility. All right, there's the notes. Let's see if we can get into some practice problems. First ones are matching. I don't think that we need to talk about that too much more. Again, these are like the same questions from the last section. You're looking for where the slope equals 0. You're looking for where it's undefined as your beginning points for this to help you out a little bit. And then from there, you're just looking for plug-in points, process of elimination, figure it out. The other thing sometimes you can do, like let's look at number 4 real quick. Sometimes you can do, if you could put the cattle chute, use your cattle chute idea. If I were to draw a cattle chute for this guy, right, it would look like this. Or something like that, right? Something like that. You could pick it vertically different. All right, so is that what I just drew, a picture of the sine graph, the cosine graph, x squared, 1/6 x cubed, or 1/4 x to the 4th? Which one does it fit? Well, it certainly isn't the sine graph because that would be a wave. It certainly isn't a cosine graph because that would be a wave. It's not a parabola. I didn't draw a happy parabola, but I did draw a cube, didn't I? I drew a cube. And so it's D. And the fourth powered one would either look like a parabola or look like a W. So you can use that too. Now, does that help you with this guy? Absolutely not. I have no idea what that graph is. Okay. Does that help you with this guy? Probably not. It might help you with one. Number one, if you remember what that graph looks like based off the choices that you've got. So sometimes you can work your way that way, trying to answer these questions. All right. The ones at the bottom, 5 and 6, they give you points. Draw the graph. Those are easy peasy. You plot the point and then follow the cattle chute, and that'll get you the picture. If I flip over, there are a couple of these that I want to do real quick. Number 8 is first on my list, and I guess number 8 kind of goes with what I just was talking about. If I go to slope field for a certain, which of the following could be the solution for this with the initial condition of 0, 1? If I'm 0, 1, I'm right here. If I were to draw the particular solution through that, again, stay within the cattle chutes or so. Which one of these equations fits that picture? Surely it's a circle. Surely it's got a center at 0, 0. Surely it has a radius of 1. And so I look at that and I say, well, only one that fits that is D. Remember the equation of a circle? X squared, or x, technically it's x minus h quantity squared plus y minus k quantity squared equals r squared. And so that's what you're doing for that guy. Number 11 is next on my quick list. Explain why the slope field cannot represent this. All right, so let's take this. If I'm looking at this, why can't this be? Now you can use a specific example or you can just be general about it. But I look at this thing, all of my y's are positive, all of my x's are positive. And this one's based off of the y's, right? Because that's what the equation is on. So if, just think about this, if y is positive, y is greater than 0, then dy over dt would be 0.6 times a positive value. So 0.6 times a positive value means that it would have to be, it would have to be, if y is positive, then it would have to be positive. I did not say that on my notes. I think I got it backwards, so let me fix that real quick. On my answer key. Okay, so if the y's are positive, and I'm just looking at the equation, I haven't looked at the picture yet. If my y is positive, then 0.6 times a positive number is also going to be a positive number. Check out all of my slope fields. All of my slope fields are going this way. Some degree of slant to them, but they're all slanted in a negative direction, which means that this is negative. That doesn't fit. So all of my dy over dt marks are negative slopes. They represent negative slopes. Therefore, 3 dots, therefore, this guy is not possible. It can't work. If I plug in any positive y value into this, I should have a positive slope out. All of my positives would be going this way, and that's not what the picture represents. And so that's a not possible. I don't think there's a whole lot more I wanted to tell you other than number 13, I know is on my list, and number 16. We got 2 to go. All right, 13's next. Here it is. I thought this might throw you off because it's asking when the slope fields are non-negative. So what does that mean? If they're not non-negative means not negative. Well, what else could they be if they're not negative? Of course, they'd be positive, but they could also be equal to 0. So that's what the question is. So you want to know, when is y squared times x minus 1 greater than or equal to 0? Now for some of these, it's a straight solution. You just take what the differential equation is. They want to know when it's positive. 2y plus 4x minus 1 is greater than 0. That would make it positive. And then you would solve it out for what y is, and then make your explanation. In this case, this one you can't just solve for y. See how difficult this one would be? But I know that it's greater than or equal to 0 if either of these pieces are greater than or equal to 0. So I know that this equation is going to be greater than or equal to 0 if y squared is greater than or equal to 0, or if x minus 1 is greater than or equal to 0. If either of those pieces are. All right, so I square root this, I get y is greater than or equal to 0. Which means that these are always positive. This is always positive. But this guy, so in other words, I don't need to include that in my explanation because it's always going to be a positive piece. This guy over here, x is greater than or equal to 1, that's when it's going to be positive or equal to 0. So the slopes, my answer to the question is, they want to know when are the slopes non-negative? The slopes are non-negative, what a weird word, when x is greater than or equal to 1. I don't need to talk about this piece because that's always going to be a positive piece. So I guess you could include it. It would be a little bit redundant, but it wouldn't be wrong to say that as well when y is greater than or equal to 0 and when x is greater than or equal to 1. But it's just you're overemphasizing that piece. All right, here comes really the last one, number 16. There was something about this I thought might throw you off. 16 says, shown above is a slope field for the differential equation, yada yada, kind of like the one we just did. If y equals f of x is a solution to the differential equation with the initial condition of 1, 2, then the limit, holy moly, what are they talking about, as n approaches infinity for the function is, and you're like, limits, we talked about eons ago. Why are they bringing up limits again? Okay, so if I look at this and I look at the point 1, 2, here's 1, here's 2. I'm kind of in this neighborhood over here for my function. Honestly, that doesn't matter a whole lot because here's what it's asking you right here. The limit as you go to infinity. In other words, if I keep going further and further and further and further to the right towards infinity for this function, what happens to my y values? They're really asking you in a hidden way where your horizontal asymptotes are. Where's your ha? Okay, so if I'm up here and I'm drawing my cattle chute and I'm going through that point, I'm kind of going like this, right? So where's your ha? Is your ha at negative infinity? No. Is my ha at negative 1? No. Is my ha at 0? No. Is my ha at 1? Ooh, that looks pretty close. Or is my ha going to infinity? And there you go. So they're asking you really where's the horizontal asymptote, but they're asking it to you in a funky way using limits. Just reminding you that that's really not as complicated as it seems. I do believe if you read that, you'd be like, what on earth are they asking me? And that's all. Where's the horizontal asymptote? Okay, that takes care of section 7.4. We are moving along at lightning speed. Thanks for your hard work, and shoot me an email if you've got questions. See you in class.